Okay, so we now can switch topic and talk about power converters. And this is another class of circuits that we need. Of course, they are particularly important in every type of systems, in particular for some specific characteristics in the type of systems that we are investigating now, which are smartphone as a typical electronic system. So in a smartphone there's typically a power delivery network, because all the different blocks of a smartphone need different types of supply voltage. And of course everything starts from the battery. Typically the lithium-ion battery in modern smartphones here, that provide a voltage of 3.7 volt when it is fully charged. And then of course from these 3.7 volts we need to obtain all the other voltages required to operate the various blocks. And in order to obtain voltages that are smaller than that one, we typically need a so-called buck converter, a DCDC buck converter. A buck converter is a switching regulator that provides a voltage at the output that is smaller than the voltage at the input. Okay, you have already seen the principle of operation of a buck converter in the first course in electronics. Now we will look at them again in order to look at their operation. For example, we need the buck converter for the CPU core, for the microprocessor. Okay, typically the CPU core needs a voltage which is between 0.8 and 0.2 volts. Okay, so the buck converter must provide different types of voltages. If you remember, this is something that I mentioned. In order to save power, the supply voltage and the frequency, the clock frequency of a microprocessor is tuned on the basis of the load of the microprocessor. So if the load is large, then one has to increase the clock frequency, and also in that case one needs to increase the power supply. But when the load is small, then it is possible to decrease the clock frequency, and therefore one in that case can also decrease the supply voltage. Of course, you remember that the power dissipation is proportional to the frequency, to the clock frequency, and is proportional to the square of the supply voltage. Therefore, if you are able to reduce at the same time the clock frequency and the supply voltage, we can strongly reduce the power consumption. And this is typically done especially for the microprocessor, which is one of the blocks which is dissipating the most power. Then we typically need different voltage for providing power supply to the DRAM. Okay, in that case one uses the output of the buck converter and then passes it through an LDO. Okay, an LDO stands for low dropout, is a low dropout regulator. Low dropout regulator is a linear regulator. Okay, a linear regulator of the type that you have seen in the first course in electronics is a series regulator. Essentially, the advantage with respect to a switching regulator is the fact that you can provide a very well regulated voltage without ripple. So very constant without ripple, which is good for the DRAM, because you want to limit as much as possible the disturb, because you have to use a sense amplifier in order to read the memory. So you need to have an actual constant voltage as a supply voltage. Okay, and this is something that is provided by LDOs. Okay? We will not discuss them in detail because most of what is important for the LDOs have been already treated in the first course in electronics. Okay, but there are also additional blocks. Typically there is an audio codec which requires 1.8 volt. The DRAM requires 1.2 volt typically. The audio codec requires a higher voltage, and again one typically has another DCDC converter, a buck, and an LDO to reduce the ripple, and then the audio. Then there is the camera, just to consider the most important one. And then there is of course the display, which actually uses a lot of power. The backlight of the display requires 3.8 volts because you need to provide power supply to some color LEDs which need larger voltage, and the camera typically needs 2.8. Okay, and again, in order to provide this voltage to these blocks, you typically have, for example, from the battery to the display, you need to have a so-called step-up converter, a boost converter, because the voltage on the display is higher than the voltage that you have on the battery. So you need to provide an increased voltage. And for the camera, well, the voltage on the camera is not so much more than the voltage on the battery, so that in that case you do not use a buck, you just use an LDO. If the LDO is not used alone, typically, because if the voltage difference between the input and the output is large, the power efficiency of the LDO is very poor. You dissipate a lot of power in the LDO. But if the difference between the voltage at the output and the voltage at the input is relatively small, such as in this case, then the LDO can have a good power conversion efficiency, and so you do not need a buck. Okay? And there are many of them for all the different blocks, because of course in a smartphone you have sensors, and then there is another piece of converter in order to provide power supply to the sensors. You have, for example, two different cameras, and therefore you have two different converters. And the reason why you have so many of them is twofold. On the one hand, you have very different voltages required, and so you want to, in order to optimize the power efficiency of the conversion, you want to optimize each buck converter to the output voltage that you need to provide. And there is also another reason, that you want to manage in a smart way the energy that you have in the battery, and if a block is not needed, you switch off the buck converter, so you basically are sure that no power is dissipated in the block. So for example, if I switch off the camera, I also switch off the regulator, and therefore this whole track does not consume any power anymore. Okay. Now, typically, what happens in a modern smartphone is that all these DC-DC converters, the buck converters, the boost converters, and also the LDOs, are all together in a single unique chip, which is called a PMIC, a power management IC. Okay, so they are all in the same, just one PMIC. PMIC stands for Power Management IC. There's a single one. In the iPhone 6 that I've shown you at the beginning of the class, actually I mentioned that there were two of them. One for all the blocks and one for the radios. Okay, but this is mostly an issue of intellectual property, because Qualcomm, which provides almost all the chips for the radio, also puts in the contract, okay, I will provide you also the PMIC for our chips. Okay, because there is also some technical reasons, because you need even less ripple in the regulators that are providing the power supply for the radios, because of course these ripples can alter in particular the detection of the signal. But in many systems you have one power management IC. So what I want to do now is look at the basics of the operation of the buck converter and of the boost converter, how they are done today, and how they work. Okay. Let me just also add that in addition to those to these converters, you very frequently have additional converters which are embedded in the chips. For example, I mentioned before the non-volatile memories. The non-volatile memories need different voltages in order to perform the program and the erase operations, the 5, 10 and 20 volts that I just mentioned before, and those voltages are typically provided by some regulators which are embedded internally, which are in the memory chips. They can be in the memory chips because they need to provide different voltages but a very small power, so they do not need to be outside. They are done specifically for the requirements of the memories inside. So from the outside you just provide a power supply to the memory of 1.5 volt, for example, but inside there are DCDC converters that transform these voltages into all the other voltages that are needed to operate the memory. Okay. Now let's look at the principle of operation, and what I want to do is to go a little bit deeper with respect to the principle that you have seen in the previous course. Okay, this is not something completely new for you, but we need to go a bit deeper. Okay. Now, so a buck converter. Buck means actually step down. This is a synonym of buck. Step down means that the output voltage is smaller than the input voltage. Okay. is a class of switching regulator and switching regulators are, let me digress a bit. Switching regulators are characterized by the fact that they have a much higher power efficiency with respect to linear regulators. And the way in which they reach this power efficiency is to have a circuit which is only consisting of reactive elements and switches. Okay? So, in principle at least, you have only reactive elements which means inductances and capacitances, and switches that can be on and off and on. Okay? Why? What's the basic idea? The thing is that, of course, ideal inductances and ideal capacitance do not have power consumption. They do not consume power. Okay, the active power consumption is 0, and also a switch, an ideal switch, does not have power consumption, because the power consumption is the product of the voltage times the current. But when the switch is off, the current is 0. When the switch is on, the voltage is 0, and therefore the product is in principle always 0. So, if you have a circuit which has only inductances, capacitances, and switches, and they are all ideal, you should have 0 power consumption in the circuit. So you should be able to pass all the power from the input to the output, and to have a conversion efficiency equal to 1. Okay? The conversion efficiency is the ratio of the output power to the input power. Okay? This is the main idea. And now we see how it is implemented for reducing the voltage, increasing the voltage, and changing the sign, and so on. Of course, this is just the ideal situation, because in practice, of course, you have dissipation in the capacitances, you have a bit of dissipation in the switches, and so on. Okay, so in the ideal situation, but the advantage of this circuit is that in the ideal situation it can have a very high power conversion efficiency. So how does it work? How can you obtain a conversion with only these elements? Let's first look at the buck converter. Typically in the buck converter, what you do is the following thing. You use pulse width modulation in order to change the average value of the voltage. You do it like this. For example, here you have a switch, and then you just this is the load, so this is external and this is the output. Okay, let's first look at the ideal situation. What you do is the following thing. You control the state of this switch. When the switch is on, the output, let's call it VO, is equal to Vin. When the switch is off, the output is 0. So if I plot it here, for example, this is T on, the time period during which the switch is on, and I have that VO is equal to Vin, and then the switch is off, and so on. This is a periodic behavior. the period is T, is the sum of T on plus T off, and the output voltage is this is a rectangular wave, but the average output voltage is V in times T on over T. This T on over T is the duty cycle. Of course, T on times V in is the area of this rectangle, and then the average V output is done by dividing this area over the period. Okay? So the inverse of this period is called Fs, is the switching frequency. Okay, this is the principle of operation. Is extremely simple. I would say is too simplified, but just we can proceed by steps. Okay, the converter does not consume any power because there is only a switch which does not consume any power in itself. But of course there are problems with this solution. It's just a first solution, and the problems are twofold. One is simple, the other one is a little bit less simple. The one thing which is clear is that actually we want a constant voltage at the output, because this needs to be a supply voltage for an electronic circuit. Okay, so of course this is good enough, but we have to filter it. Okay, we have a square wave. The average value is proportional to the duty cycle, which is this T on over T is defined as the duty cycle, is the ratio of the positive wave to the total period. And of course, if you want to have only the continuous component, we need to filter the output voltage. So we need to filter the rectangular wave. This is the easy part. Then, in addition to that, there is also something which is not actually so easy, and that is this fact. Of course, you can imagine that the current through the switch, when the switch is turned off, goes abruptly to zero. Okay, this is typically not advisable because, for example, we can have an output which has an inductive component. For example, if the load is a small motor, then the load has an inductive component. If you instantaneously switch off the current of an inductive component, this voltage goes deep down in order because an inductive load is inertial with respect to the current. So the voltage adjusts in order to continue to receive current, and then you typically have an over voltage on the switch that typically can cause problem. Okay, you can have an excessive voltage on the switch during the switching, during turning off, that typically causes damage to the switch. Okay, so we do not want to stop instantaneously the current through the load. Well, there's no reason to do that because actually here we want a constant voltage in principle. Okay, so we need to change a bit the circuit while keeping the most important aspects, and this is actually what we do. So by putting everything together, we want to, on the one hand, we want to filter the output, and on the other hand, we want to let's say have a continuous current through the load, and this is actually what we do. this is the solution. Basically, we need to add an inductor, a capacitor, and a diode. Now the situation is simple to understand. This is a low-pass filter. And the cutoff frequency of the filter is cutoff frequency of the filter is 1 over 2 pi square root of LC. This is L and this is C. And if you want to use it as a low-pass filter, this frequency must to be much smaller than the switching frequency. Okay, so that you cut the switching frequency and all the other harmonics on the output, and you only have the constant voltage. This is air out, this is VO, and this is V in. And the diode is used to enable current to flow, also when the switch is off. What happens is that when the switch is on, the current can go through the switch in this direction, but when the switch is off, this inductance continues to drive the current, but the current can go from the diode. So typically is just sufficient that the inductance put this voltage down to 0, so that the diode starts to conduct, is turned on, and the current can flow in this direction. Okay? And this is what happens. So the diode avoids any voltage spike on the switch, because as soon as the voltage on this point goes to 0, the diode is turned on and current can flow. Okay, so again, the operation is completely identical to what we have said before. The output voltage on average is T on over T times V in. This is the duty cycle, but in this case the output voltage is much closer to the to a completely constant quantity. Okay, it's much closer to a completely constant quantity. Typically what we have is that if I take this voltage here, the voltage here has the same shape that we were discussing before. During T on, V1 is equal, this is V1, V1 is equal to V in, and during T off, assuming that the diode is ideal, V1 is equal to 0, so this is V T off, and this is T, but the output is after this low pass filter, and therefore we have at the output only the constant component. So VO is constant, is the average of V1, so that we have already computed before. So this typically is also the output. There is no reason to put the angle brackets to specify that it's an average, because more or less it's constant. Okay, there is a slight variation, because of course the low pass filter is not ideal. It suppresses the harmonics but does not eliminate them. Therefore you have some slight ripple, but for our purpose it can be neglected. Okay. Now, of course, you can see that if you change the duty cycle, you can change the output voltage. If you change the value of T on with respect to the total T, you can adjust the output voltage more or less as you want. Okay. Now, one thing that is interesting is to look at the current through the inductor. Okay. The current through the inductor is, let us call it IL, and of course it can vary significantly. Now you should consider that the constant part, the average part of the current through the inductor is exactly the current through the output load. Okay, because the average current through the capacitor is 0, and therefore the average of IL is the output current. Okay, now let's look at how IL is doing. Now IL depends on the voltage applied to the inductor, and of course there is a simple relationship between the voltage for an inductor. There's a simple relationship between the voltage applied to the inductor and the current through the inductor. Okay, it is the relationship which defines an inductance, and is this one: VL is equal to L times the derivative of IL over time. Okay, so if VL is positive, we have that the derivative of the current with respect to time is positive, which means that the current increases linearly. On the other hand, if VL is negative, we have that the current decreases linearly, because the derivative of the current with respect to time is negative. Okay? Now, in this case, what we have is that since V in is larger than VO by definition, when the switch is on, the voltage applied to the inductor is positive, because V in is larger than VO, and the current increases. When the switch is off, the voltage applied to the inductor is negative, because in this point is 0, and on the output terminal is V out, and so the current is decreasing. Okay, let's draw these expressions. So during T on, VL is equal to V in minus VO. Okay, so this means that the derivative of the current with respect to time is equal to, of course, VL over L, and therefore is equal to V in minus VO over L. On the other hand, when during the time in the time during which the switch is off, VL is equal to 0 on one hand and VO on the other hand, so it's equal to minus VO with the sign that we had chosen, and therefore the derivative of the current, which is VL over L, is equal to minus VO over L. Okay, that is the situation. If we want to draw VL in time and IL as a function of time, we have the following thing. Okay, let's assume that this is T on and then this is T off. Okay, as before, and this is T and this is 0. During T on, this is V in minus VO. During T off, this is minus VO, and then again. Okay, because this is periodic. As far as, okay, it's not nice. if you consider it carefully, this must be more negative than this is positive because T off is smaller. Now, okay, T on and T off I already drew. For the current, it's this thing. When during T on, the derivative of the current with respect to time is V in minus VO over L. So it is this one. Okay? So constant slope, constant derivative. During T off, it's negative, and it is again. This is okay. I do not have a ruler, but of course is a straight line. This is negative. Okay, and of course the thing is periodic, which means that this has to be exactly equal to this one, because if we are in a stationary situation, all behaviors are periodic. Okay. Now we can exploit this situation in order to evaluate what is the difference with respect between the output voltage and the input voltage. This is relatively easy because I can compute the increase in current from T on, and I can compute the decrease in the current during T off, and the two things must be equal. Okay, so this increase in current during T on is the derivative V in minus VO over L times T on. Okay, this is delta I. Okay, but of course this must be identical to the same delta I computed during T off, which is minus VO over L, which is the derivative of the current with respect to time, times T off. So the two things must be identical, and of course once I have them, I can extract VO and have it as a function of V. Okay. Now, in order to simplify things, I can use only T on, so T off can be written as T minus T on. And of course, if I put together the first and the last expression, I have L, which I can simplify. And of course, if I extract VO, I can write something like VO so also this one and this one go away, so I have VO is equal to T on over T times V in, which is exactly what I had already written without looking at the current. Okay, this is something that we had already written. Now, so in the inductance, I have a current which is increasing and decreasing during a period, and at the output I have a constant voltage. And this means, of course, that let me just go back one slide, that the constant part of IL goes through the R out, the output resistance, because the voltage is constant, so also the current is constant. And the alternate part of the current goes through the capacitance, because of course across the capacitance no constant current can pass. Okay, so the IO, the output current, is exactly the average of IL. Just to draw everything, the average of IL is I out, which is V out over the resistance at the output, the load resistance. Okay? Now, this is the, let's say, extremely simple part. Okay? It's easy to understand what's happening here. If we change the duty cycle. We change T on with respect to T, and then we can change V. If, for example, the battery discharges, then what happens is that the voltage of the battery is reduced, because this is what happens during the discharge of a battery. If you want the same output voltage, the only thing that you need to do is to increase a bit the duty cycle in order to compensate the decrease of the in. This is what happens typically in a buck converter. Now, the other the tricky thing that we need to take into account is that if the output current required by the law is reduced, what we have is that this plot here shifts vertically, okay, because the average value of the current is decreasing. But at some point, if the current goes down, what can happen is that this point can touch zero, or at least if we continue to use this model, it can go below zero. But of course, the current cannot be negative, because it has to pass through the diode, which cannot let the negative current pass, because the current in the diode can only pass in one direction. Okay, so we need to consider what happens at very low output current. So the principle that we need to consider is that first let us focus on the limit of continuous conduction, when the minimum current in the inductor is 0, and let's look at this situation. Okay, and then we see what happens if we reduce further the output current. So, in the limit of continuous conduction, the current in the inductor goes like this. This is T on, this is T off, this is T. Goes like this. Is 0 at the minimum, so it's still continuous, but we are at the limit. Okay? And then in the other half wave, it goes down to 0, and so on. Okay, we can compute this limit, because of course we know that the quantity that we have called delta I in the limit, so in the limit, the quantity that we have called delta I is equal to 2 times the output current. That's it. So this simple expression can tell us what's the limit. So we can write it. We have delta I was equal to V in minus VO over L times T on, and this is equal to 2IO. Okay, but of course we know that what do we know? We know that VO depends on V in. VO is equal to T on over T times TE times V in. Okay, and we can substitute this expression into this one in order to remove the output voltage from this expression. Okay, we can probably simplify things if we call this ratio B, like duty cycle, and therefore T on becomes like D times T. So that if you make a substitution, we have V in times 1 minus D times D over L times T is equal to 2IO. And then we can compute the current. So current, this is the current at the limit of continuous conduction. So we have, you see that the current is something which is not absolute, but depends on the duty cycle. So I output is equal to V in times T times 2L times D times 1 minus D. Okay? So if we want to plot the output current as a function of D, we have something like a parabola with a parabola with the concavity down, something like this. Of course it is a parabola, of course the coefficient, the second order coefficient is negative, and when D is equal to 0 the current is 0, but also when D is equal to 1, which is the maximum value, the current is 0. So the parabola is like this, and the maximum you have when D is equal to 1/2, and this is easy to compute. Okay. So you can write it like when D is equal to 1/2, this product is 1/2 times 1/2, which is 1/4. So we have something like V in. We can write something like this. IO max times 4 D times 1 minus D, where IO max is equal to V in times T over 8L. Okay, this is interesting because this part at maximum is equal to 1 when D is equal to 1/2. So this IO max is the maximum value that the current at the limit of continuous conduction can have. Okay? So, if we reduce the current, at some point we reach the limit of continuous conduction. The point is, what happens then? What happens after the limit of continuous conduction? I just want to use 1 minute to tell you this aspect. Below the limit of continuous conduction, we are in discontinuous conduction. In discontinuous conduction, what happens is that the current is 0 for a finite time. In practice, we have this situation. This is VL, this is IL, so let me repeat this fact. During T on, VL is equal to V in minus VO. During T off, VL is equal to minus VO. Okay? So this is a period, everything repeats periodically. Now, if the current is small, what we have is the following thing. During T on, the current increases. During T off, the current decreases. At some point, it touches 0. When it touches 0, it cannot go negative. Okay? Because if you look at the circuit we have here, let me show it here. When the switch is off, the current passes through the diode, and of course cannot be negative because the diode is stopping the current. Okay? And therefore it goes to 0. So it goes to 0, and then it increases again. Okay? So we have a significant part during which we have 0 current. There are no spikes because the current goes to 0 gradually. Okay? So there are no spikes, but still the current is going to 0. So of course the discussion that we have done before, the calculations we have done before in order to compute the relationship between the output voltage, the input voltage, and the duty cycle does not hold anymore. Okay? We have, if we want to make a complete calculation, we have to consider that the whole switching period has to be divided in 3 different phases. We have T on, and then we have T off, which is in turn divided in 2 different intervals that we can call delta 1 and delta 2. And during delta 1 the current goes down, but during delta 2 the current is off. The current is 0. Okay? So, and this is important. Why this is important? This is important because of course the way of regulating the voltage must change at these very low voltages, because regulating the output voltage, just adjusting the duty cycle, knowing that the duty cycle is the ratio of the output voltage to the input voltage, is not true anymore. Okay, and this is a situation which did not used to be very typical in let's say it was not very typical in the switching regulators of desktop computers, for example, but it is extremely typical of portable electronics, because in portable electronics you typically want to put everything in standby when you do not need it. Therefore you have rapid drops of the current required from the regulator, and then you need to adjust, because very easily every switching regulator can go from a continuous conduction mode to a discontinuous conduction mode. Okay, I do not have time to address this issue, but okay, we can spend some more time next time. But of course I want to, let's say, highlight the issue that probably you do not have seen. Okay, we stop here.